right, so the deer population has at the park is 330. So at N0, we have 330. And at N1, we have 420. So that's going to help us down the road. The increased deer population from year N-1 to N, or we would go X of N minus X of N minus 1, is going to be 3 times as big as going from X of N minus 1, or X minus 2 to X of N minus 1. So we're just subtracting X of N minus 1 minus the previous. So these are the previous. From this one to previous is 3 times this one to previous. What does that make you think of as far as a relationship? Exponential, right? So don't you think there'll be exponentials in this answer? So what we're going to be getting to eventually is we're going to be changing this x to n into an at1 to the nth power, an exponential, plus bt2 to the nth power, which is an exponential. That's what we're going to be building on for part B. But this one's quite easy. All you have to do is go x of n minus x of n minus 1 equals 3x of n minus 1 minus 3x of n minus 2. So when we solve for x of n, how many x of n minus 1s are we going to have? 4 of them. And how many x of n minus 2s are we going to have? Still negative 3. Does that look familiar? Oh, yeah. That's what we have for that. Now, why did they say n is greater than or equal to 2? Right, because when you're using 2 previous, you got to start at 2. All right, now solve the occurrence relation. So this is, the tricky part of this is that we need to get so that x of n minus 4x of n minus 1 plus 3x of n minus 2 equals 0. We're going to put that all there. And then we're going to move everything up. I don't know, I'm not sure how to describe this, but they're going to refer to x of n as 2 above this one, 2 powers above. So we're going to use 2t to the second power minus 4t plus 3. Now remember, did we do something like, did you multiply by like x of 2? That's what they did. It was like x of 2 or t of 2 or something. That's why this one got bigger by 2. This goes up by 2. This goes up by 2. This goes up by 2, leaving that. Does yeah, there was a way that we did it. Like we're substituting maybe. T was equal to x sub n. Is that possible? And then t squared, or oh, I know what it was. T squared was x sub n. T was, yeah, somehow the t's worked in there. I can't remember right offhand. Anyway, now you're going to factor this to find out what t is, to get these values of t that we're going to be putting in here, t1 and t2. So you'll get t, what is that going to factor into? Negative 1 and 3. Yep. So t will be equal to 1 and t will be equal to 3. We usually put the 1 first. So we're going to have x of n is equal to a. t1 is 1 to the n. And t2 is 3 to the n. Next, we're going to use that information that we had up here. N0 is equal to 330, and n1 is equal to 420. So you needed two different informations to get this x of n. Here we only need one piece of information to get my x of n. That's the whole point. So let's say we have x of 0 is equal to 8. Well, what's 1 to the any power? 1 plus b times 3 to the 0 power. Now, what's x0 equal to? Or n0? n0 or x0? 330. So one of my formulas will be 330 equals a times 1 plus b times 3 to the 0. What will the next formula be? A times 1 to the 1 plus b times 3 to the 1. That's equal to 420. So this is going to be 420 a plus 3b. Stop. Turn to your neighbor. Tell them how you're going to get this far with both parts. Go. Ready to solve for a and b. So I'm going to take the opposite of these, add them up. I get 2b. A minus a is 0. 420 minus 430 is 90. So b is equal to 45. A would have to be equal to a plus 45 has to equal 330, right? 285, yeah. So a is going to be 285. So what we just did is we developed a formula that says x of n is equal to 285 times 1 to the n. Well, 1 to any power is what? 1. And then it's going to be plus b, which is 45 times 3 to the n. That is my equation, recurrence relation. That's the equation that we have. And that comes from way back when we had x of n was equal to 4x of n minus 1 minus 3 x of n minus 2. Yep, that's what we're going to do next. Yes, sir.
So this.
Great, that went awesome. Now we're going to prove this using strong induction. So what's the first step in any math induction? Check for n equal to what? 0 or 1. We're going to do 0. So if we took this first one, x of 0 is going to be equal to 285 plus 45 times 3 to the 0, which is, what is that? 2 or 330. That's what we had originally. And then if we did x1, we'd get 285 plus 45 times 3 to the first, which should be your 420. Well, we do because now what we're going to do is we're going to check this against this x of 2, which is going to be 4 times x1 minus 3 times x0. So 4 times 330 minus 3 times 420, what is that equal to? Actually, we need an x2 here too. How much? Just 60? Are you sure? So then x1 should be equal to 285, or x2 should be 285 plus 45 times 3 squared. That should not be 60. 9. Oh, this should be plus. That's my mistake. Oh, wait, no, this is minus.
So wouldn't it be 4 times 420 plus 8 times 350?
Yep, I got them backwards. All right. Thank you. 420 minus 3 times 330, and what do you get for that? 690. And if you did 285 plus 45 times 9, what do you get? 690. So therefore, these are the same. So we checked that at the original. Then we're going to do the n equal to, then we're going to do n equal to k. And the n equal to k term, we want to, all right, the one that we want to check is going to be the x of k is equal to 285 plus 45 times 3 to the k. What will x of k minus 1 be? X of k minus 1. What will that be? 285 plus 45 times 3 to the what? K minus 1. Good. So now what we're going to do is we're going to take this one and we're going to check n equal to k plus 1. Yeah, we had to. It'll totally make sense when you see it in just a moment here. Was that k minus 1 though?
Oh, yeah.
Okay. So we're going to check for n equal to k plus 1. So that formula was x of k plus 1 is 4 times x of k minus 3 times x of k minus 1. Are we good with that? Then you're going to substitute. Take your yellow, substitute it in here. Take this blue, substitute it in here, and we'll find out what x to the k plus 1 is. Here goes. X, k plus 1. This is kind of cool because I remember those formula ones, the algebra was really icky. But look at how nice this one is. 4 times x of k, 285 plus 45 times 3 to the k, minus 3 times, now this blue one, 285 plus 45 times 3 to the k minus 1. When I multiply that out, I'm going to get 4 285s and 4 times 45, 3 to the k's. I'm going to subtract 3 285s. Please don't multiply those out unless you dislike yourself. Minus 3 times 45 times 3 to the k times what? 3 to the k minus 1 is 3 to the k times 3 to the negative 1, right? Or 1 out of 3. Does that make sense? Because it's 3 to the k minus 1. 3 to the k times 3 to the negative 1. So what will happen here is that these will cancel out. And so you're going to get 4 285s minus 3 285s. And by the way, how many 285s is that? 1 285. Then you're going to get minus or plus 4 times 45, 3 to the k's, minus 145 times 3 to the k, because these 1/3 and 3 cancel out. If I have 445 3 to the k's minus 45 3 to the k's, how many 45 3 to the k's is that? That is plus 3 times 45 times 3 to the k. So we can say this is 285 plus 45 times 3 to the k times 3 to the 1. What's a quicker way of writing 3 to the k times 3 to the 1? Oh. What just happened? Therefore, true for n equal k plus 1. Now, because of this, now we can write our final since statement. Therefore, I'm going to use their words here. Since true for k and k minus 1, it is true for k plus 1. Also, true for k equals 0 and k equal 1. It is true for all k, that's the strong part, then proved by strong math induction. Let me help you with that a little bit. So you're saying it's true for k and k minus 1. We did that to get this. It's true for k and k minus 1, so it's true for k plus 1. What you did was here you showed where it was true for k and k minus 1. Then, using that relationship, you showed that it was true. Sorry about that. Why is this not helping me? There we go. And then we showed that it was true for x of k plus 1. So it was true for k and k minus 1. Then it was shown to be true for k plus 1. Also for k equals 0, k equal 1, it was true for all of k. Then it's proved by math induction. So it's this little part here that you're annoyed with, and I am too, that makes it strong math induction. And that's problem number 3.